Every year, the world grows more than 15 million tons of hemp to produce ultra-durable textile fibers, automotive composite materials, and even Hempcrete, a lightweight, insulating, and nearly carbon-negative building material. So how do we plant, harvest, and transform this seemingly simple plant into applications that go far beyond what anyone imagined? The journey begins in vast hemp fields, where the stalks are harvested at their optimal stage and fed into processing systems calibrated with micron-level precision. The long outer fibers become premium textile material, while the spongy inner core, which makes up nearly 60% of the plant's mass, is transformed into hempcrete, a highly insulating, bio-based material that is steadily making its way into the specifications of major construction projects around the world. And today, join Agriculture Insight as we explore how hemp, once dismissed as a wild weed, has risen to become one of the most promising sustainable materials of the 21st century. Hemp isn't a common plant for most Americans, but the truth is there are far more surprising and fascinating things about it than people realize. In the materials industry, hemp is considered one of the few crops that can truly solve the sustainability equation. Producing 1 kilogram of fiber requires only about 1,500 liters of water, while cotton consumes 13 times more, and polyester relies entirely on petroleum and leaves behind microplastics. Not only that, 1 hectare of hemp can absorb 2 to 4 times more CO2 than a tropical rainforest, making it one of the most powerful carbon-capturing machines humans can cultivate. With advantages this obvious, many people wonder, why hasn't hemp grown as strongly as other materials? The answer lies in the very first doubt you probably had when looking at its leaves. For nearly 70 years, cannabis plants were lumped together under narcotics legislation, even though industrial hemp has no psychoactive effect whatsoever. Ironically, cotton, nylon, and paper manufacturers only intensified the stigma through lobbying efforts designed to keep hemp banned and eliminate a far more sustainable competitor. It wasn't until the global shift toward bio-based materials and the United States officially legalized hemp in 2018 that this buried ace card was finally revealed again. Modern fiber processing technology has pushed hemp to a new level. As soft as cotton, as breathable as linen, yet stronger than polyester. Today, global hemp cultivation has surpassed 770,000 hectares, and the hemp fashion market alone is nearing $6 billion, a milestone proving that the era of sustainable materials is no longer a promise, but a reality already gaining momentum. The journey of every hemp plant begins with millions of seeds being sown into the soil each April and May across Colorado, the hemp capital of the United States. With its dry climate, large day-night temperature swings, and an average elevation of over 1,500 meters above sea level, the region offers ideal conditions for fast germination, straight stem growth, and the highest fiber content throughout the plant's cycle. Before reaching the fields, the seeds are cleaned, graded, and pre-germinated in trays to ensure uniform quality. Thanks to automated seeders capable of handling around 200,000 seeds per hour, farmers no longer have to plant by hand, cutting labor needs by more than 70%, while keeping planting density perfectly calibrated for each production purpose. From there, hemp grows rapidly. In just over a month, the rows close their canopy, covering the field as the plants enter their biomass building stage. Another month later, they shift into reproduction. Leaves widen, small flower clusters appear at the stem tips, a signal that the plant has completed its vegetative growth. The optimal time to harvest hemp is late summer, when more than 6,500 hectares of industrial hemp in the San Luis Valley simultaneously reach ideal height and biological maturity for producing bast fiber and woody hurd. At this stage, Specialized harvesters are brought into the fields, machines capable of cutting stalks close to the ground, preserving their full 2.5 to 3.5 meter length, and aligning them in a single direction during operation. This cut and line technique minimizes stem twisting and breakage, reduces bast skin damage, and preserves more than 80% of fiber value right at the field. After cutting, the machine spreads the stalks evenly across the field to ensure a stable retting process. Natural dew retting, driven by moisture and microbial activity. Standard retting takes 2 to 6 weeks, depending on soil humidity, nighttime dew, and temperature fluctuations, all of which affect how quickly the pectin layer bonding the bast and hurd breaks down. By maintaining the integrity and tensile strength of the bast fibers, the proportion of stalks meeting spinning grade quality increases significantly, boosting productivity to over 5 tons of dry stalks per hectare, a level manual labor can hardly achieve at scale. Unlike harvesting hemp for fiber, which requires keeping the stalks long and intact, harvesting hemp for hemp cement, Hempcrete doesn't require taking the whole plant. Instead, growers use forage harvesters or specialized hemp decortication harvesters. These machines operate using a high-speed rotary cutting system at the front, slicing the stalks into short segments as soon as they enter the intake. After that, a hammer mill or chopping drum further processes the stalks, breaking them down into small pieces ranging from 5 to 25 millimeters, the optimal size for separating out the hemp hurd, the lightweight woody core used in construction materials. The shredded material is then carried upward by an auger conveyor directly into the machine's rear collection tank, or transferred into a towed trailer for transport to the decortication facility. And now we've arrived at the most exciting part of today's video, the process of transforming hemp into high-performance, next-generation materials. The production of Hempcrete begins with separating the woody core from the outer fiber. After harvesting, the hemp stalks are fed into a decorticator, where counter-rotating rollers and crushing drums mechanically break down the stalk, peeling the bast fibers away from the hurd through compression, shear forces, and continuous oscillation. Immediately afterward, a system of screens and air separators automatically filters out short fibers and impurities, retaining only clean, uniformly sized hurd with its structural integrity intact. After being screened, the hurd is fed into a dry mixer to loosen the fibers and increase aeration before combining with the binder. Immediately afterward, hydraulic lime or hydrated lime is added at the standard ratio of 1 part hurd, 1.5 parts binder, and 2 parts water. This ratio is specifically formulated to allow easy shaping and mineralization while preserving the hurd's natural properties, porosity, lightness, and its inherent ability to regulate moisture. After that, the mixture is placed into molds or an in-situ casting system according to the designed thickness. Each layer is lightly compacted and leveled to achieve moderate density, while still maintaining moisture release and air retention capacity. When it comes to real-world construction, Hempcrete is used in 2 main ways. For projects with standardized designs, builders rely on precast blocks and panels. The mix of hemp hurd and binder is molded, dried, and delivered to the site. Workers simply install these units onto the structural frame and wait for them to set. Fast, clean, and with consistent quality control. The second method is more flexible and suited for projects that require on-site shaping. Hempcrete is used as a lightweight concrete that can be applied or sprayed directly onto a pre-assembled structural frame. Compared to using precast blocks, casting Hempcrete in place creates a seamless, monolithic wall with no joints, resulting in better thermal retention, reduced heat loss, and a clearer expression of Hempcrete's natural ability to regulate temperature and humidity. A house built with on-site hempcrete typically takes around 7 or 10 days to dry and set. In return, the walls can withstand over 2 hours of continuous fire exposure, are non-combustible, produce no toxic smoke, and do not weaken structurally. In addition, this material continues to absorb CO2 throughout the building's lifespan, helping the house stay cooler in summer and warmer in winter, a key reason why it has already been adopted in more than 40,000 buildings across Europe and North America. Beyond its role as a bio-based construction material, hemp holds another, far more common potential hidden just beneath its soft outer bark: hemp fiber, a natural fiber that is several times stronger than cotton. After several days to weeks of field retting, the dried hemp stalks are transported to the processing facility, marking the official beginning of their transformation from an agricultural crop into an industrial raw material. At the intake gate, any stalks that are curved, have a moisture content above 18%, or are fractured will be rejected. Immediately afterward, the remaining stalks enter the decorticator, but instead of retaining the woody hurd. This entire process is designed to separate and preserve the long bast fibers, the only component used for fiber production. At the critical stage, the bast fiber bundles enter the carding system, where thousands of steel needles on counter-rotating cylinders continuously disentangle, deep clean, and stretch the material. Each hour, a single production line can perform over 20 million micro-carding actions, generating a level of fiber-separating force and precision that no manual tool could ever achieve. With every pass through the machinery, the fibers are straightened, fully separated from hurd particles and impurities, and stripped of short, non-standard segments. The result is a stream of smooth, parallelized fiber slivers with stabilized length, officially entering the next stage of high-precision processing. After carding, the sliver is still soft, uneven, and lacks fiber structure, so it is sent through the drawing system. Here, multiple slivers are drafted and combined into a single, uniform strand to equalize density, adjust tension, and stabilize the dimensions of the roving before twisting. Once the sliver is stabilized, it enters the spinning stage, the process that ultimately determines yarn quality. The first step is roving, where the sliver is gently twisted to form a semi-finished strand, strong enough to withstand drafting without breaking. This roving is then transferred to the ring spinning stage, where it is further drawn out, reduced in thickness, and tightly twisted to create the final yarn, meeting industrial standards for tensile strength, fineness, and twist. At modern operating speeds, a single ring spinning machine can produce over 150,000 meters of yarn per hour, transforming loose, disorganized fibers into uniform and stable yarns, ready for the subsequent weaving and dyeing processes. At the end of the production process, the finished fibers are wound into large spools, each stretching from 8 to over 25 kilometers, depending on manufacturing standards. At this stage, hemp fiber is fully processed and technically complete, officially becoming a feedstock for textiles, biocomposites, cellulose engineering, and various forms of industrial reinforcement materials. Leaving the factory, hemp fibers enter supply chains in more than 30 countries, with the fashion industry consuming over half of all output. And although hemp is not yet as mainstream as cotton or polyester, full collections made entirely from hemp fiber have already begun to appear. Few people realize that if somewhere in a landfill, you find a t-shirt that decomposes completely within just 6 to 8 months, there is a good chance it was made from hemp. Even more remarkable, every ton of discarded hemp fiber continues to absorb nearly 2 tons of CO2, creating a net positive environmental impact, rather than contributing to degradation like most other fibers today. Do you know what truly gives a dollar its value? compared to an ordinary piece of paper or cloth? It's not the ink, nor the imagery, it's the design. A sophisticated security architecture embedded in every tiny detail. Before any bill comes into existence, its journey begins with a sketch created by the most skilled engravers at the U.S. Bureau of Engraving and Printing, B. Every element, the presidential portrait, the phrase "In God We Trust," geometric patterns, or the blank space for a watermark, is designed as a layer of security. These experts are bound by lifetime confidentiality, even after retirement, because revealing a single detail could provide counterfeiters with a critical loophole. Once the sketch is finalized, it is transformed into an ultra-high-resolution laser engraving, ensuring that each denomination has a completely unique set of identifiers. But design is only half the story. The rest begins in the cotton fields of the southern United States. Over 2/3 of a US dollar structure is made from cotton, a special fiber that forms a steel frame giving the bill strength, durability, and near-tear resistance. To achieve this quality, the US doesn't use ordinary cotton. They grow specialty cotton in southern states like Texas, Mississippi, and Georgia, where the hot, humid climate produces long, pure white fibers far stronger than standard textile cotton. During harvest, high-capacity machines collect more than 2,000 kilograms of cotton per hour, but only about 10 to 12% meets the standard for currency production. The bales are then sent to processing plants, where the entire production line operates almost entirely automatically. Machines remove plastic wrapping and feed the cotton into the system. Rotating shafts with comb-like teeth fluff the fibers, removing dry leaves, small stems, and dirt. Next, compressed air and vibration mechanisms clean fine dust before the gin separates the seeds, keeping only the purest layer of fiber. While the textile industry allows up to 5% impurities, cotton for currency can contain no more than 1%. Even a tiny piece of leaf the size of a pinhead can cause the system to reject an entire 200 kilograms bale. Everything must be perfectly clean before being sent to the paper mill. To increase durability and resistance to twisting, the US also adds linen fibers. Most of the linen for US currency is imported from France and Belgium, where centuries-old flax fields produce long, fine, and exceptionally uniform fibers. The flax is harvested using specialized machines that pull the entire plant from the ground, rather than cutting it, preserving the full fiber length, a key factor in a bill's strength. Bundles nearly 1 meter long are laid in parallel on the fields to air dry naturally for several weeks. Once the fibers reach the ideal ripeness, machines roll them into large bales weighing around 300 kilograms. From there, the flax undergoes a sophisticated processing routine to extract the fibers perfect for currency paper. In the fields, it is left to rot naturally for 2 to 4 weeks, a form of biological soaking where bacteria and natural yeast break down the plant's pulp, separating fibers without breaking them. An interesting fact, the retting process must be monitored daily. Extending it by just 48 hours beyond the ideal can weaken the fibers by 20 to 30%, enough for them to be rejected for currency production. Finally, the flax passes through crushing and combing machines, which remove the woody core. The resulting high-quality fibers are pressed into bales and sent to the paper mill. When the raw cotton and flax bales arrive at the mill, the journey to create the world's most secretive paper officially begins. The white fibers are cleaned with steam, chopped, and blended in large vats like a thin porridge, where ultra-fine security fibers and invisible industrial DNA are mixed in, forming a base that no counterfeit printer can replicate. The mixture is then poured onto conveyor belts, pressed thin, dried, and rolled into large sheets of paper. Each sheet already contains watermarks, security threads, and extremely precise technical features. The paper is then dried, pressed, cut into large rolls, and sent to the U.S. Bureau of Engraving and Printing, BEP. This is a proprietary security paper, never sold on the open market, and only Crane Currency in Massachusetts is authorized to produce it under contract with the U.S. government. The paper is ready, but a dollar truly begins to exist only when the steel engraving is created. In the BEP's engraving room, artisans sit before gleaming steel plates, using pantograph pens to carve every detail, so meticulously that some spend 3 weeks perfecting a single strand of hair. From Franklin's forehead wrinkles to the tiniest decorative patterns, every line must be absolutely precise. Once completed, the master plate is chrome-plated to withstand tons of printing pressure. Even a deviation smaller than a hair can result in its immediate destruction. But one engraving alone is not enough. From the master, the steel plate enters the serography system, where every detail is copied so precisely that the human eye cannot distinguish it. The plate is then coated with fluorescent powder, exposed to UV light to reveal the image, and placed in an electroplating bath, where electric currents carve grooves just a few microns deep. The result: electroplated steel plates that are 20 times more durable than the original, able to endure tens of thousands of printing cycles under tons of pressure. Each plate perfectly identical and ready for the currency printing line. Once the steel plates are ready, another production line simultaneously kicks off. Offset printing to create the first background layer of the bill. This initial layer forms the colored background, including watermarked patterns, light color overlays, and decorative borders. At this stage, high-speed printing machines print both sides of the paper simultaneously using special inks. The ink is transferred from the printing cylinder to an intermediate rubber layer, then pressed onto the paper fibers, ensuring even adhesion and sharp, precise details. This technique is applied only to denominations $2 and above. The $1 bill skips this step entirely, which is why it feels different to the touch. The personnel working in the currency printing facility are among the most rigorously vetted in the U.S. Spotless backgrounds, pass lie detector tests, and possess ultra-fine precision skills. All activities are monitored 24/7, and AI is allowed only to assist, never replace human operators. After the background layer is fully dried, the sheets are stacked and sent to the intaglio printing stage. Using the hand-engraved steel plates replicated through serography, each plate is mounted onto an intaglio press, applying 20 to 40 tons of pressure, enough to crush an iPhone. Under this immense force, ink is pushed out of the steel grooves and onto the cotton linen surface, forming the raised texture and the distinctive, real money scent that every counterfeit note fails to replicate. And once the intaglio printing is complete, the bill moves on to a completely different layer of security. OVI color shifting ink, a technology guarded like a military secret. OVI ink appears only on denominations $10 and above, yet it is one of the most visually recognizable security features. Tilt the bill slightly, and the number 100 shifts from a copper hue to green right before your eyes. This effect comes from a multi-layer structure containing ultrafine metallic crystals that act like nano mirrors, reflecting light at precise angles. The technology is so tightly controlled that only a handful of countries and suppliers, primarily a CPA of Switzerland, are authorized to produce it. Even central banks are never allowed to possess the raw ink. They receive only the exact amount required for each print run, and that ink has never existed on any black market. Once the OVI layer has sealed the surface with its signature color-shifting effect, the process still isn't over. The bill moves on to an even more intricate layer of security, one so small that it's nearly invisible to the naked eye. Microprinting. Microprinting is the art of hiding text in the most sophisticated way on a US dollar. On the $100 bill, you'll find the phrase, "The United States of America," delicately engraved into Benjamin Franklin's collar, while the tiny USA rests just beneath his portrait. So small, you'll need a magnifying glass to see it clearly. If you're holding a $100 bill, try checking it now and see how sharp your eyes really are. These miniature characters are printed with specialized inks and micron-level engraving plates. To the average person, they look like decorative patterns, but to experts in currency inspection machines, they are the first, fastest, and hardest to fake line of defense against counterfeits. Once the microprinting layer has finished its role as the subtle gatekeeper, the bill moves on to its final stage, the part that is, ironically, the easiest to counterfeit, printing the serial numbers and treasury seals. In this step, a specialized printing system stamps each bill with 2 unique serial number sequences, giving every note its own identity. At the same time, 2 important seals are printed on top, the U.S. Treasury seal and the Federal Reserve seal. This is also one of the few elements that criminals can attempt to mimic, since serial numbers use flat ink without raised textures or complex security structures. Passing off a fake is one thing, but getting through quality control is a completely different battle. Right after the identity layer is printed, each bill enters one of the strictest inspection systems in the entire process. Ultra-high-resolution optical sensors scan every millimeter, catching anything from color shifts and ink bleeding to a single misprinted serial digit. Raised ink, color-shifting OVI, and microprinting are analyzed in mere milliseconds. Even the tiniest deviation sends the bill straight to recycling. Finally, a manual inspection team randomly checks bundles to ensure no subtle flaw slips through. Only the bills that pass this brutally strict inspection phase earn the right to move on to the final stage, cutting and packaging. Each sheet of currency is printed in large formats, with 32 complete $100 bills on a single sheet. After inspection, they're fed into an ultra-precise cutting system that slices them into individual notes with exact dimensions of 6.14, 2.61 inches. The blades are so sharp that even a deviation of a few microns can disqualify an entire batch. The finished bills are then stacked into bundles of 100, pressed flat and grouped into bricks of 1,000. Every brick is tagged with its batch code, production date, and traceability data, all instantly digitized for auditing and storage. Today, the world produces more than 300 billion rolls of toilet paper every year, and this massive industry generates over $60 billion in global revenue. In the United States alone, the average person uses about 100 rolls per year, most of which are produced domestically. Familiar names like Charmin, Cottonelle, Scott, and Quilted Northern dominate the market, turning toilet paper into a true multi-billion-dollar business. And if you were at the supermarket, how would you choose your toilet paper? By brand, by the claims printed on the package, or simply by which roll feels right at first glance? And now, let me take you to the southeastern United States, where the subtropical climate and year-round rainfall have nurtured vast eucalyptus forests, meticulously planned and cultivated specifically for the paper industry. Each tree takes up to 20 years to mature. When the trunk reaches a diameter of 10 to 12 inches, with moisture below 60% and optimal cellulose content, it's ready for harvest. When the harvest season arrives, the forest comes alive. Massive harvester-forwarder machines, each weighing nearly 18 tons, move into action. First, hydraulic arms clamp the tree trunk tightly, while a chainsaw blade slices cleanly through the base in just seconds. The trunk is then lifted and fed through an automatic delimbing unit, where rotating rollers strip off branches and bark. Next, laser sensors determine the precise length and send data to the machine's control system. The log is automatically cut into even sections, roughly 2 meters long, the ideal size for transport and later pulp processing. The entire sequence takes only a few dozen seconds, requiring almost no human touch. Yet every move is tracked by GPS to ensure cutting stays within designated zones and avoids disturbing the forest floor or young roots. Even the machine's tracks are engineered to distribute weight evenly, preventing soil compaction and allowing the forest to recover quickly after harvesting. Most of the wood used for toilet paper is considered low-grade timber, crooked trunks, young cores, or blemished logs unfit for furniture making. Yet this very wood has the perfect balance of fibers and lignin for pulping. On average, 1 ton of eucalyptus can yield about 700 kilograms of paper pulp, and on an industrial scale, a single plantation like this can supply toilet paper for millions of people each year, all without touching a single natural forest. As the first trees fall, the next star of the forest takes the stage, the forwarder, a timber hauler capable of carrying up to 14 tons of logs in a single load. In other words, with just about 70 trips, more than 1,000 tree trunks can be transported to the collection site. Despite its massive, almost beast-like frame, the forwarder moves with surprising grace. With a hydraulic arm and a mechanical grapple that can rotate a full circle, it grips, lifts, and stacks bundles of logs weighing hundreds of pounds with precision, a mesmerizing mechanical dance in the heart of the forest. From here, the journey to transform those rough wooden trunks into soft white sheets of paper begins, as the green forest connects seamlessly to the mill through a transport network stretching for miles. When the timber trucks arrive, the journey begins anew in a very different way. Here, the logs enter the first stage of the paper-making industry. Thousands of tree trunks are unloaded onto vast yards spanning hundreds of hectares, where they are sorted, measured, and stacked into towering rows, forming walls of wood that mark the true beginning of their transformation. Every sheet of paper begins with pulp, but before it becomes pulp, each tree trunk must first be chipped into wood fragments, a process that seems simple but serves as the first true test of precision. Inside an industrial chipper weighing several tons, steel blades spinning at up to 700 revolutions per minute slice the logs into perfectly uniform wood chips, each measuring only about 2 to 3 centimeters in size. Here, uniformity is everything. If the chips are too large, the chemicals won't penetrate evenly. Too small, and the cellulose fibers will break apart. The entire operation is monitored by optical sensors, transforming what once seemed like a brute mechanical step into a fine display of technological precision. After that, the clean wood chips are pumped into a high-pressure digester, where a mixture of alkaline chemicals and heat breaks down the lignin, the natural glue that binds cellulose fibers together. Over roughly 3 hours of cooking, the lignin dissolves, leaving behind an ivory-white suspension of fibers, a thin, milky liquid that is, in fact, pulp. From a single batch of 25 tons of wood chips, the mill produces about 15 tons of high-quality pulp. The leftover black liquor, rich in dissolved lignin, is recovered and burned to generate energy for the mill itself, completing a closed-loop cycle of material and energy. The final step before this humble pulp begins its transformation into toilet paper. However, compared to virgin pulp, which consumes vast amounts of energy, water, and forest resources, recycled paper offers a far more sustainable path for the toilet paper industry. It can cut energy use by up to 50% and save 70% of water for every finished sheet produced. Yet, turning old paper into new material is no simple journey either. Recycled paper is collected from all kinds of places: offices, stores, printing houses, but not every sheet can make it back into the production cycle. At the mill, an automated sorting system takes on a task that seems simple, but demands incredible precision, separating paper from plastic, cardboard, metal, and debris. Using near-infrared sensors, the system scans each piece of paper to identify its material composition. And in a fraction of a second, bursts of compressed air blow away unwanted particles from the conveyor belt. Thanks to this technology, a single production line can handle up to 400 tons of recycled paper per day, creating a clean, consistent source of raw material, the foundation for everything that follows. Recycled paper, once sorted, is fed into an industrial shredding machine. Inside, counter-rotating steel blades pull the paper inward and tear it apart through continuous cutting, producing thousands of small uniform pieces just a few centimeters wide. The speed and spacing of the blades are automatically adjusted according to the paper's thickness and type. The entire process is enclosed, ensuring the paper is loosened and separated layer by layer, ready for the next stage of pulping and de-inking. After being shredded, the paper is sent to the processing area, where it enters a massive industrial washing system that runs through 14 continuous treatment stages. Here, layers of cellulose fibers are released from their original structure, ground into a fine pulp, and pass through multiple filtration screens to remove even the tiniest impurities. Next, the pulp moves into centrifugal cleaning chambers, spinning at extremely high speeds to separate heavier particles such as sand, metal fragments, or small pieces of wood. Though this process demands a significant amount of energy, it's still considered far greener than producing virgin pulp from wood, with each ton of recycled paper saving dozens of trees and thousands of liters of water. Even after cleaning, the pulp still carries the traces of its past, ink. To remove it, the pulp is mixed with a special soapy solution. As the mixture is stirred, countless tiny bubbles rise to the surface, lifting microscopic ink particles that cling to the foam. The dark froth is then skimmed away, leaving behind a cleaner, ivory-colored pulp beneath. Finally, the pulp undergoes a mild bleaching process and is diluted with water, forming a smooth, milky suspension, the purified pulp, ready to be reborn as paper once again. At the heart of this process stand massive machines over 120 meters long, running day and night, carrying out 4 remarkable stages of transformation that turn nothing more than water and cellulose fibers into paper. The pulp is diluted and pumped onto a continuously moving mesh belt known as the fourdrinier wire. As the slurry spreads evenly across the surface, water drains through the mesh, leaving behind a tightly interwoven network of cellulose fibers, the very first rough form of paper. At this stage, both the shape and strength of the sheet are determined. Even the slightest deviation here will leave its mark throughout the paper's entire lifespan, much like the foundation of a building. At this point, the paper sheet still contains dozens of times its weight in water. To remove this excess, it passes through a series of press rollers, each weighing several tons and operating under extreme pressure. As the sheet moves through, it is tightly compressed, forcing out moisture while strengthening the bonds between cellulose fibers. Continuing its journey, the wet paper sheet enters a system of massive heated drying cylinders, or long drying tunnels, stretching dozens of meters, where high temperatures evaporate the remaining moisture. Under the intense heat, the cellulose fibers contract and bond more tightly, forming a continuous sheet of dry paper that races forward at more than a mile per minute. This stage consumes the most energy, but it is also what determines the paper's whiteness, strength, and stability. Once it leaves the dryer, the paper still carries wrinkles and ripples caused by heat expansion and contraction. It then passes through a series of calendar rolls, where heat and pressure are precisely adjusted to smooth the surface, create a gentle sheen, and ensure uniform thickness. The result is a soft, even ribbon of paper, winding gracefully around the Yankee dryer drum, the final step before it's cut, embossed, and packaged. All of this happens in just 7 seconds, from a watery slurry to fully formed sheets of paper, light as air, yet born from hundreds of tons of force and thousands of sensors. After all that, the long sheets of paper stretching hundreds of meters are sent to the winding and cutting section, where the final shaping and packaging take place, turning them into finished products. Massive rewinding machines, each over 80 meters long, can process up to 500,000 rolls per day. The paper is then embossed with delicate micro-patterns, creating its signature dotted texture, a design that not only softens the surface, but also enhances thickness and absorbency. Once completed, the rolls are cut, wrapped, and packaged, ready to enter a global distribution network spanning more than 190 countries, where every day, billions of people begin and end their routines with this seemingly humble product. In specialized farming regions, tappers begin their work quietly from midnight to dawn, when the air is cool and moist, and the latex becomes thicker, smoother, and flows most evenly. The latex vessels always run from upper right to lower left, so the tapping knife must be held at a precise 45-degree angle to follow the correct direction. Before tapping, workers mark 3 to 4 guiding lines using a pen and measuring tool, or press a plastic stencil against the bark to ensure perfect alignment of the cut. When the knife is drawn, its thin curved blade slices only about 1 millimeter deep, just enough to reach the latex vessels without touching the wood. A slight slip of the hand can cause the tree to bleed, dry out its latex vessels, or lose vigor. The latex drips into aluminum or corrosion-resistant plastic cups hung about 15 centimeters below the tapping cut, close enough to catch the entire flow, yet far enough to avoid contamination. After 4 to 6 hours, the cups fill and are collected into larger containers. Over time, the cups build up an oxidized rubber film, which must be cleaned regularly. A skilled tapper can work 400 to 500 trees in a single morning, the result of years of practice to master the rhythm of each stroke, the exact depth of the cut, and the distinctive snap sound of latex vessels being opened. Across southern Thailand, thousands of small factories work day and night to press fresh latex into latex sheets. Thin, pale, flexible, and resilient layers of rubber that carry the vitality of the tropical forest and serve as the foundation of the global rubber industry. As soon as the fresh latex arrives, it is roughly filtered and poured into large aluminum trays. Workers stir it thoroughly to disperse the latex particles, then add a formic acid solution, the catalyst that helps the latex coagulate quickly. Within just a few minutes, the liquid begins to solidify into a smooth, soft, milky white mass. The surface is carefully leveled to ensure uniform thickness before the block is removed from the mold. This marks the very first step in forming a complete latex sheet. Once the latex has coagulated, each sheet is removed and rinsed in a water tank to eliminate any remaining acid. The sheets are then fed through a rolling machine, 2 heavy steel rollers spinning in opposite directions that press the rubber flat and bring it to the correct thickness. With every pass, water and impurities are squeezed out, making the rubber clearer, more flexible, and more elastic. The fine mesh-like patterns that appear on the surface are the hallmark of a properly rolled latex sheet. After rolling, the wet sheets are hung outdoors to dry. Depending on the weather, this air drying process takes 1 to 2 days. At this stage, the rubber has become strong enough to fold, roll, or move without tearing. The dried sheets are then moved into the smokehouse. Smoke from smoldering firewood or wood chips drifts through the chamber, both fully drying the sheets and tinting them with their signature amber color. This process also provides antibacterial protection, prevents mold, and enhances durability. When they step out of the smokehouse, each sheet has taken on a golden hue, flexible, tough, and ready to be baled for shipment. Once they reach the proper dryness, the latex sheets are pressed flat, graded, and bundled into neat, square bales. From there, they are sent to major factories, where these golden brown latex sheets will be transformed into tires, gloves, or durable shoe soles. All of them begin with a stream of white latex deep in the forest. Farewell to the smoky, wood-scented workshops. In modern factories, natural rubber latex is reborn as the core of some of the world's finest premium mattresses. Unlike memory foam, natural latex is inherently antibacterial, breathable, hypoallergenic, and offers outstanding elasticity and longevity. That's why, in the luxury segment, a king-size latex mattress can reach prices of up to $2,600 USD. First, natural latex is combined with various additives such as foaming agents, stabilizers, sulfur, and accelerators. This mixture is blended thoroughly in specialized mixers to ensure uniformity and achieve the desired physical and chemical properties. This step determines the mattress's elasticity, durability, and its ability to form a stable foam structure in the next stages. Next, the uniform latex mixture is poured into a specialized mold fitted with metal rods called pincore pins, which create ventilation holes throughout the mattress. These holes enhance elasticity, airflow, and breathability, helping the mattress stay cool and comfortably supportive during use. Inside the vulcanization chamber, the latex mixture is heated and subjected to high pressure. The very breakthrough that gave birth to the modern rubber era more than 180 years ago. Heat and sulfur create cross-links between the polymer chains, transforming the soft, sticky liquid latex into a solid mass of elastic, stable, and durable rubber. Thanks to this process, the mattress core maintains its shape, resilience, and consistent foam structure for many years, a key requirement for it to qualify as a true industrial-grade product. When the process is complete, the mold is carefully opened after 1 to 2 hours of cooling. At this stage, the mattress is still soft and warm. Even a slight pull or a sudden impact can tear the surface, damage the ventilation hole structure, or cause deformation. For that reason, every movement must be slow, steady, and perfectly coordinated to ensure the mattress maintains its shape and surface integrity. After demolding, the mattress passes through a continuous, gentle washing system using clean water. Large rollers rotate slowly to turn and lightly press the latex block, allowing water to wash evenly across the surface while pushing out foam residue and impurities. This step ensures the mattress is not only thoroughly clean, but also safe, hypoallergenic, and user-friendly. The clean mattress then travels along a conveyor into a temperature-controlled drying chamber, which removes all remaining moisture, prevents mold growth, and preserves both the natural elasticity and stable foam structure. Before leaving the factory, each mattress is tested using an automatic pressure compression machine, a device capable of simulating tens of thousands of real-life sleep cycles. The machine repeatedly compresses and releases the mattress in a standardized rhythm, precisely measuring its sinkage, elasticity, and recovery ability. All data is recorded automatically. Only the products that pass this rigorous evaluation are approved for packaging and distribution. After passing inspection, the mattress is packaged with protective wrapping, vacuum sealed or rolled, depending on the model, then labeled, sealed, and shipped, ready to begin its journey to the consumer. In 2024, the global natural latex mattress market was estimated at about USD 10.6 billion, reflecting a growing demand for durable, sustainable, and high-quality sleep products. Leading brands like Avocado and Latex Co. have successfully embraced this trend, building their reputation on natural latex cores that are safe for health and deliver an exceptional sleeping experience.